Okay, so basically, for example, if the bottle is open, so this means some like inside there's some water, so the water vapor can be exchanged between the system. This is the system, okay, and the environment, and also the heat can also be exchanged between inside and outside. So this system is called open system. Open system. So the open system means it can the mass and the energy can be exchanged between the system and the environment. Okay, and if the bottle is closed, so this means this mass can be exchanged, but the heat can be exchanged between the system and the environment. So this kind of system is called a closed system. Closed system. And if like in this thermal flask, so in the thermal flask, so this means no heat can be exchanged between the system and the environment. And also here is also closed. So this system is called isolated system. Isolated system. So basically, when we studied when we studied the system, basically using the third one. Okay. So this is about the system. There are three kinds of systems. We introduced the for some reaction, they like release heat. If the release heat is called exothermic process. So this, for example, after this reaction, the system will release energy to the surrounding, to the environment. And for some reaction, they absorb. They should accept heat from the environment. So this is called endothermic process. So the surrounding provide heat to the system. Okay, we also introduced this, right? So basically, we can use if the energy, the y-axis is energy. We know all substances have energy. So if the energy of the products is lower than those of reactants, so this means it will release heat to the surrounding. If the energy of the products is higher than that of reactants, so this means the system should absorb heat from the environment. So this is about the exothermic and endothermic process. Just this is decided by the energy difference between the reactants and products. Okay, we also introduced the thermochemistry is the study of heat change in the chemical reactions. So this is about the thermochemistry. So it studies the heat change. Okay, and the thermodynamics is the study of the interconversion of heat and other kinds of energy. We know besides the heat, there also may be some other kinds of energies. So these energies can be exchanged, can be interconversed each other. So the study of the interconversion of the heat and other kinds of energy is called thermodynamics. So here there are two different concepts. Okay. So what are the state functions? So state functions are the properties that are determined by the state of the system. regardless of how that condition was achieved. For example, energy, pressure, volume, temperature, all these are called state functions. State functions. For example, these two guys, okay, they go from this point to here. So the energy difference from here and here is certain, right? It's certain. So the energy is a state function. Is state function. Also, for example, it doesn't matter which way he used, right? So in this picture, for the height, so from here to here, the height are different, right? So the height is state function or not. The height. But not the height here, okay? The height is function, is a state function or not. So it's for example, the height it depends on the road or not. It's not, right? So the height is also a state function. No matter which way he goes, right? The height is certain. So the height also a state function. So this is about what is state function. State function. So here is for the potential energy. Here, these two guys have the potential energy, right? So the potential energy also the same, right? So it doesn't matter which way he used. Okay. So this kind of concepts is called state function. State function. Okay. Like the volume, just it depends on the final minus the emission. It doesn't how to change the volume. Right? You can use a different way to change the volume, but the volume is a state function because it's only decided by the final state and the initial state. Okay, it doesn't matter the process. So this kind of pressure, volume are state functions. So any question for state functions? Okay. Now introduce the first law of thermodynamics. So first law of thermodynamics is about the energy can be converted from one form to another, but can't be created or destroyed. So this means the energy will not lose. Okay, will lose. It can only be converted from one form to another. Okay. So for example, after this reaction, it will release energy, right? It give out heat. Okay. So the heat will be received by environment. Okay. The heat will not only just go, okay, just go, but it will, in fact, it will accepted by the environment. So this means the energy cannot be destroyed, right? So after this reaction, we can see some chemical energy lost by combustion, right? After this reaction, some chemical energy lost by combustion. But this energy equal to the environment gained, the energy gained by the environment. Okay. For example, after the reaction, if the system, this is the system, reaction system, if the system lose 100 kilojoule. So the surrounding will gain the same number of energy, right? So we can say if lose is minus, but here is plus. So here we can say the system, the energy change of the system, and the energy change of the surrounding should be equal 0. So this is about the first law of thermodynamics. First law of thermodynamics. So this means the energy can be converted from one form to another. So in this case, so which kind of energy is changed to which kind of energy after this reaction? So for this reaction, there's some chemical energy, right? Chemical energy. So the chemical energy is changed to what kind of energy? Yeah, heat. Yes. So this means the energy can be converted from from chemical energy to heat, okay, but cannot be destroyed. Or like we can use this. So the system, delta E system equal minus delta E surrounding. Okay, because if one lose, so one should gain, should accept. Okay, so this is about the first law of thermodynamics. Now we introduce the enthalpy and the first law of thermodynamics. We know the enthalpy is used to quantify the heat flow into or out of a system in a process that occurs at a constant pressure. So we introduced this before, right? So for example, for each substance, we can find its enthalpy. You don't get the book. If you have the book, you find the book. All the substances have enthalpy. Okay. So for a reaction, we can just for the enthalpy change of reaction, we can just use the enthalpy of products minus the enthalpies of the reactants, and then we can get the change of enthalpy for a reaction. So like this, okay. So because the enthalpy of water in liquid is higher than that in solid, the difference there difference between these two states is 3.01 kg per mole. So this means when solid water, the ice, is changed to liquid water, it need absorb this number of energy from environment. And in this reaction, we can see the enthalpies of products are lower than those of reactants. So after the reaction, some chemical energy will be released, okay, and the environment will get the chemical energy. Okay, so we know this is about enthalpy, right? So now introduce the relationships between the enthalpy and the first law of thermodynamics. So here we introduce the thermochemical equations. Thermochemical equation means like we need to use it this way to describe the energy change after the reaction after a reaction. Okay. So for example, for this reaction, so we can like solid ice change to liquid. So here is the enthalpy change of the reaction. So here the number is positive. Positive. So this means the system, this is the system, right? The system gains heat from environment. So the energy of the system is increased. Is increased. So the number is positive. It's positive. Okay. So here, for this, in this equation, we can see the enthalpy change of the reaction is negative. Is minus, right? So this means after the reaction, the system loses some energy. So the energy change is minus. Is a minus number. Okay. So here we can see here is minus or plus, means the system lose or gains the energy from the environment.
So if it's minus, it loses.
Your question?
If it's minus, it loses.
Before.
If the value is minus,
yeah,
it loses.
Yes, the system loses some energy. Okay. If we use plus, so this means the system, the energy of system increases. Okay. So this is about the system's energy change. Okay. Minus means the system loses. Okay. And it's positive, it means the energy, the system gets energy from the environment. Okay. So this is about the thermochemical equation. Okay. And you also can find this kind of equation in the book. Okay. For all reactions, it has like a enthalpy change for this reaction, and of course this enthalpy change is about the chemical energy change. Okay. Okay, and of course for the reaction we need the stoichiometry coefficient. For example, we know, and also the direction of the reaction is also important. For example, from the solid to liquid, it needs ice. If ice melts, it should get energy from environment. So, yeah. So the enthalpy change is plus, right? But if the liquid change to solid, and the number is the same, but here is changed to minus, because when the liquid changes to ice, it will release energy, so the system loses energy. Okay, and if the reaction is like multiplied by a number, for example, 2, if 2 more change to 2 more, so the enthalpy change should also double. Okay, should also double. Yeah.
So look at the fact that the boiling point and the melting point are two different things. Why should the energy be the same? Because if solid changes to liquid, it means, yeah, heat 100 degrees for it to, I mean, I don't know how to explain it. I mean,
You mean why this lamp are same, right?
yes, looking at the fact that one has to move from solid to liquid, isn't that?
Okay, we're going to do this more later. Because this is about the reaction is, because the reaction is reversible. So this means it's a balance. It's a balance, for example, this is melting point, right? It's the melting point. At the melting point, some solid will change to liquid. And you can also say some liquid can change back to solid.
Yes.
And so the energy for these two processes as the number of C as C. Okay. And if you like each time, each side times like 2, so also the energy should also double. Okay. And also we need to be careful their state. The state is also important. We must write out the states of the substance, of some liquid, solid or liquid or gases, okay. Because the substance with different states have different energy. Okay, so you must write out its state. For example, the air, the liquid water, and the gaseous water, their energy are different. Okay, so you must write out their state. Okay, the question: how much heat is evolved when 266 grams of white phosphorus burned in air, like in this reaction? Okay, so for this thermal reaction, thermochemical equation. This is thermochemical equation, right? And this is balanced. And the change of the reaction is this number. Okay, so how to calculate when 266 grams of white phosphorus burned in air? You can say the unit is this energy, right? Per mole. This is 1 mole. 1 mole will release this energy. Now we need to calculate this mass. So how to do it? Yeah?
No. Okay. I'm not sure.
It's okay.
I'm explaining.
And you
Then you get to enjoy.
we trust you.
Since
Because you are monitor.
Okay, since we are given number, the heat change, right? And he gave us the grams. The question. Yeah, we are given the mass. So in order to get the energy, the heat, yeah, how much heat? In order to get the heat, we have kilojoules per mole, which kilojoules is the heat energy. So we do mass over mass to get number of moles of phosphorus. What's the mole mass of phosphorus?
Yeah, tell him.
Google.
Google it. Oh.
First man.
It's okay.
Again.
No, I didn't see.
Okay. We have seen now.
Or
Try it on the other hand.
I don't know how to do it. What is that thing called? We use this one.
Just wanted to see this.
Ah,
You know, that's
so
what I showed.
what's the number of moles?
More.
Yeah, more mass of phosphorus.
120.
123. 0.889. 120.
Just wait, 123.9.
124.
Okay, yeah, that's 120.
Yeah. Yeah, mass over 1. So 266. Divide. 266 divided by 124.
2 point something.
2 point what?
Uh,
2.1.
2.145. Yeah. So this one, 3, 0, 1, 3 equals to 1 more. Yeah. How about 2.145? Yeah. Then you cross multiply. You get the answer. That would be the image fit.
Okay, good. Yeah. Okay, you get it. Okay, thank you. How to remove? Yeah.
So wait. Yeah.
Okay.
I want you to wait. You I have questions. It's okay. You ready?
You can ask.
You ready?
You
You
got
can ask. I remember.
Oh.
Okay, so you said 313. I mean 313. I mean 30138. That one, it's one more of what's given.
Yeah. Per more.
That's the
Right.
average for one more.
Per one more. Like when somebody says per something, it
And-
means per one thing.
And all the Vesa units are like that. Does it mean that number is kind of like a mixture of that?
Yeah, a mixture, not a
Like
mixture.
that.
If it's kilojoules more, that's the mixture. But if it's per more, it's a division.
So kilonewton per meter, what do we do?
If it's 200 kilonewton per meter, that means 200 kilonewton per 1 meter. So maybe if
But
you're
we
given
still
a
do the
100,
division one by we do the stuff where we actually use the meters, right?
yeah, that's when you divide now by that those meters, maybe
Exactly.
5
My
or
point
10.
is we divide it by those and not just that one. So here.
Oh no, usually don't divide, we multiply. To get
Yes,
the force.
that's the same idea I'm trying to bring. We are using that number and not just pay 1 watt. Just here saying all that is just pay 1 mole. So meaning all that is equal to 1 mole.
Yeah. 4.
Yeah,
It's
but-
not equal
But that's
to
the
1.
set function. The answer would be the same.
Like it's usually when we multiply. Okay. The moment when you are given the when you are given the moment, right? It's kilonewton per meter. But when you are told to find the force, maybe on a 5 meters of a beam, what do? You multiply. It's the same as maybe 200 kilonewton equals to 1 meter. How about 5 meters? That's the same thing.
Yes.
Yeah.
That's why we multiply the distance.
That's why we multiply.
Look, understand multiply the distance and everything, yeah?
But here also we multiply.
The answer would be the same. The answer would be the same.
Okay, say that.
Yeah, the answer would be the same.
Yeah, that's it.
Let's just say that because me I'll argue with the
Yeah, the answer would be the same.
I'll give you a lot of scenarios here.
Someone's crush.
Okay. So here you can see here's the number. Cohesion number is 1. Okay. So this is 1 mole of phosphate exponent in L will give this heat. This heat. Okay. Now we know the mass of the phosphate. So we need to change the mass to more number. Okay. And then this is the more number of the phosphates. So this is 1 mole, but now the more number is this one. So just times this, and we get this number. We can use this way to calculate the energy released. And here should be careful with minus. The minus means the system loses energy. Okay. So any questions for this? Okay. So this table to show some the reactions and there are changes. So we can say for this acid-base reaction, because this is acid, this is basis, right? So acid-base reaction, so it can release heat. And but for this process, it will gain and heat from the environment. Okay, and we also can see the ice changes to liquid. We need energy. Okay, and also the liquid, the water changes to gaseous water. So it also need energy. Okay, so this sample, when we use this sample, we should careful if there are conditions. So this sample are obtained at 25 degree. Okay. Okay. So here is about the specific heat of a substance. So specific heat of a substance is the amount of heat required to raise the temperature of 1 gram. 1 gram. The mass is 1 gram. Okay. And the temperature is just 1 degree. Raise 1 degree. Okay. So this is the specific heat. So for example, we know the water. The water says its specific heat is 4.184 joule per gram per degree. So what does this mean? According to this concept, what this number means? What does this mean?
That's the amount of energy required to raise 1 gram of water by 1 degree.
Right?
That number is the amount of heat required to raise 1 gram of water by 1 degree.
Very good. Yes. Yeah. This number is the heat required to raise 1 gram, for 1 degree for 1 gram of water. Okay. So from this sample, you can see this is metal, right? These two are metals. This carbon, these are metals. We can see the water. This sample is much higher than others, right? So what does this mean? So this means it's more difficult to raise the temperature of water. For other substances, it's very easy. For example, for the metal, okay, if for 1 gram, if we raise their temperature by 1 degree, they only need very few heat, and water needs much more heat. So this is why the water can be used to cool the machine, okay, like a car, okay. So in the car, you're using water, right? And of course, it's not pure water. They also added some chemicals inside, but basically it's water, because the water can absorb, can gain more heat from the environment to increase its temperature. Okay. So this is about the specific heat. Heat capacity of a substance is the amount of heat required to raise the temperature of a given quantity. So given quantity means differences. Here is 1 gram, right? But here is a given quantity. Is maybe not 1 gram. Okay. And the temperature also by 1 degree. 1 degree. So the heat capacity, we can say C equal M. M is the mass of the substance, times the S. S is the specific heat. Okay. So this is the heat capacity. So heat capacity is this. And the heat absorbed or released, Q, we can like using this equation to calculate the heat absorbed or released for a substance. M is the mass of the substance. Okay, S is specific heat. We know specific is 1 gram, right? This is about 1 gram. But now we time the heat of 1 gram. Now it's not 1 gram. Now it's the mass is M. And also the delta T is the difference of the temperature. Now it's also maybe not 1 degree. In this case, it's 1 degree, right? 1 degree. We also can so this MS is C. So and the temperature change is under minus the initial. Okay, so question. How much heat is given off when 869 gram iron bar cools from 94 degree to 5 degree? We know the specific heat of iron is 0.444 joule per gram per degree. So how to calculate? So basically we can use this equation, right? So the heat is means each heat equals the mass, and this is specific heat and the change of temperature. Now here, okay, we know the specific heat of iron. No, you have answered. Yeah, no,
I don't know.
you don't know? Okay, that's fine. Okay, your turn.
Yeah, so from the formula.
Okay.
You don't know how to think about it.